Today we're going to be talking about titrations, and the place that I want to start today is by talking about indicators. So acid-base indicators change color based on the pH of the solution that they're in, okay? And these are either weak acids themselves or weak bases themselves. So if we say that an indicator is a weak acid and it's monoprotic, let's say it's HIN. Now, IN doesn't stand for indium, IN just stands for indicator, okay? So I'll show you structure of an indicator in a moment. This is going to establish an equilibrium in water with hydronium ion plus IN minus, okay? Now, we know that water is colorless. And if water just picks up one more proton, it is still going to be colorless. These things have color because they're actually fairly large carbon-containing compounds, organic compounds. Okay? So if I take this indicator and I put it into an acid, let's say HCl. I know that when I put HCl into water, what I get is H3O plus Cl minus. Now, what does that matter? Well, I create H3O plus, and this H3O plus is part of this equilibrium, which means I'm going to get a little bit of common ion effect. The presence of this H3O plus is actually going to push equilibrium back towards HIN. And if we do this with phenolphthalein, what we're going to see is that the solution is colorless. So that means that this HIN is in fact colorless. Okay? Now, as I add base, I know that sodium hydroxide in solution forms sodium ion plus hydroxide ion. Okay? The hydroxide ion is going to react with this, all of this hydronium ion now that's in solution, and we're going to get a neutralization reaction. So hydroxide ion plus hydronium ion yields 2H2O. Okay? So that, in effect, is going to take some of this H3O plus, and it's going to decrease the concentration of H3O plus, which means equilibrium is going to shift towards products because the concentration of this has gone down. That's my stress. Okay, so that's going to shift equilibrium this way, and the solution starts to turn pink, fuchsia. Okay, so that means that IN minus must be pink, and that's in general the way that these acid-base indicators work. So these things, like I said, are rather large molecules. So this is phenolphthalein, okay, and it's actually diprotic. It can lose this proton and it can lose this proton, okay. This is bromthymol blue, okay, and again, this is another diprotic weak acid. Okay, it can lose both of these, and even though some weird stuff happens here, but the bottom line is this: you lose this hydrogen here, and you end up with a negative charge here. You lose this hydrogen here, you end up with a negative charge here. Okay, so two different structures, two very different structures, and so one of them is yellow, and the other one is very blue, okay? So, but the bottom line is that I just want you to have in mind that, like, this would be H2IN, and this would just be IN2 minus, okay? So just keep these things in mind as you're going forward. The pH range over which an indicator changes color is called the transition interval. So the transition interval for, let's say, methyl red is 4.4 to 6.2. So 4.4 to 6.2. So it changes color over these intervals. So in the acid, it's pink, and in the base, it's kind of like a light yellow kind of colorless idea. The one that we use a lot is phenolphthalein, which is colorless in acid solutions, and pink, fuchsia, in base solutions. Okay, so what you want to try to do is you want to try to match up the correct indicator to your titration, which I'll talk about in a moment. So what is a titration? Well, a titration, the definition your book gives you, is a controlled addition and measurement of the amount of solution of known concentration required to react completely with a measured amount of a solution of unknown concentration. Okay? That's a lot of words. Really what it means is you're using a known solution to determine the concentration of an unknown solution. And for acid bases, this relies on neutralization. So remember, we could write neutralization two ways. H3O plus OH minus reacts to form 2H2O, or H plus OH minus yields H2O. Okay? And remember, we can use these sort of synonymously. They both describe the same process. The point at which two solutions used in a titration are present in chemically equivalent amounts is the equivalence point. So usually we'll be doing an acid, so let's say HCl plus NaOH yields NaCl plus H2O. Okay? The point at which the two solutions used in the titration are present in chemically equivalent amounts. You've been in chemistry for almost an entire year now. You should be able to look at this and tell me, okay, by chemically equivalent amounts, we're probably talking about equal number of moles, right? Yes, that is correct. So the point in a titration at which an indicator changes color is called the end point of the indicator. So ideally what you want is you want the end point of the indicator to be at the equivalence point of your titration. All right? So using an acid-base indicator is one way to do it. Another way to do it is to use a pH meter. So we'll take a look at this. HCl plus NaOH, this titration again, yields Na plus Cl minus plus H2O. Okay? And I'm writing this way for a reason. All right. Now H2O, we know that this is neutral. Okay? This doesn't affect pH. And chloride ion is the conjugate of this strong acid, which means it's weak. Okay? So this shouldn't have an effect on pH either. This sodium ion is the conjugate of a weak base, which means it also shouldn't have an effect on pH, or a very little effect on pH, which means that if I react 1 mole of this with 1 mole of this, the solution should be neutral, which means that the equivalence point should happen around pH 7. So in fact, I did this titration curve, okay, using a pH meter, where I started out with acid, HCl solution, and I added base to it. And what you'll see is nothing happens, and then all of a sudden it changes really fast, and then nothing happens again. Okay? So the equivalence point is in here. Now, when you have a titration curve like this, okay, the equivalence point is actually the point where the slope of the tangent line, for those of you who know what I'm talking about, is at a max. So the maximum, where the tangent line has a maximum slope. So that's going to be somewhere right around in here. Okay? And that's right around pH 7. So I did this right. Yay. Okay. So that's strong acid, strong base. Well, what happens if I have a weak acid, strong base? So weak acid, the one that they always use is acetic acid, right? HC2H3O2 plus NaOH is going to yield H2O plus Na plus C2H3O2 minus. Now, here's my H2O, okay? That has no effect on pH. This shouldn't have an effect on pH, but this is the conjugate base of a really weak acid, which means that this is decently strong. Okay? Now, what does that mean? So the reason that this is decently strong, or the reason that that matters, is this is in the presence of water. A whole lot of water, right? This all happens in solution. Okay? I generate hydroxide ion. Okay? And the fact that I generate hydroxide ion is going to increase my pH at the equivalence point. Okay? So here, the equivalence point is going to be, the pH is going to be greater than 7. Okay? And it has nothing to do with the fact that this is a strong base. Okay? It has to do everything to do with the fact that this is a weak acid. So its conjugate is actually a decently strong base. So if I'm asking you to explain something like this later, I don't want to see any mention of this sodium hydroxide. I want to see you talking about this weak acid, the conjugate of which is a strong base. Okay? So if I draw my titration curve now, it's going to look something like this, where I add my sodium hydroxide, and now my equivalence point is going to be a little higher than 7. Okay, I'm not going to expect you to be able to find exactly where that is, but I want you to know greater than 7, less than 7, or 7. Okay.